Now, the next property of light, the next concept here, let's call frequency. This is the one you guys were mentioning a little while ago. Frequency. And the variable we're going to use for frequency is just a lowercase f, okay? So frequency represented by a lowercase f. And frequency is not something you can draw, okay? It's not something you can just look and see. But let's figure it out. Okay, if I say something is frequent, what does that mean? If I say this thing is frequent, what does that mean? This happens frequently. Yeah, it happens often. It happens often. If something is frequent, it happens often. And if it's infrequent, it doesn't happen often. So I was going to ask, therefore, if frequent, actually I'll go ahead and ask it, if frequent means it happens often, and infrequent means it doesn't happen often, can you guys figure out what frequency means? What is frequency? The frequency of an object is, or the frequency of some event is. Actually, somebody already said it, so I'll go ahead and go with that. It's how often it happens. How often? Yeah, that's right. That's right. The frequency is how often, or yeah, basically there's a bunch of ways to say that. Okay, one moment. Got some buzzing going by. Can you guys hear that lawnmower? Yes or no? Is it overpowering my voice? Or can you guys still hear me? Can you still hear me? Okay. Sorry about the lawnmower. It's very loud for me. So again, just give me a I can't hear you if you can't hear me, okay? All right. So, frequency. We just said frequency is how often something happens, okay? So, imagine I'm standing here, okay? And let's just look at wave B for a second. Imagine I was standing here, and well, actually, you know what? Let me get over here. Let's say I was standing right here, and wave B was passing by me. If I counted how many waves passed me per second, remember this is a bunch of waves, one after the other. If I count the number of waves that pass me per second, that would be the frequency of that wave. It's how often a single wave passed me. The number of waves that pass me per second would be the frequency of this wave. Okay, so I could sit here and be like 1, 2, 3, 4, 5, as each wave went past me. So the frequency of a beam of light is the number of waves that pass per second. So what is the unit for frequency? Let me get myself out of the way. Does anybody know what the unit for frequency is? Well, actually, let's put it this way. Here's the unit. It's per second. It's 1/seconds, which another way to say that is per second. Okay? So if I say that a beam of light had a frequency of 10 per second, I'm saying 10 went past in a second. Okay? And if another beam of light sent more waves past per second, it might be 100 per second or 1,000 per second. But there is another word for a per second, and it's written like this. Hz. Another way to write a per second is written Hz. Do any of you guys know what Hz stands for? Does anyone know what Hz stands for? Hertz. Okay? A hertz. So the hertz is the same thing as the per second. It's just named after someone. It's named after a scientist who studied light, okay? In other words, 1 hertz is the same as 1 per second. So let's see if we can understand this here. If I told you we had a beam of light, and that beam of light had a frequency of 100 hertz, how many waves does it send past me per second? Okay? If the frequency of a beam of light was 100 hertz, how many waves would pass per second? 100. Exactly. So all hertz means is the number per second. And you may have seen on electronics, you may have seen something like a kilohertz. How many hertz would a kilohertz be? If something was measured in kilohertz, how many waves are passing in a kilohertz? Or kilohertz? Remember, what does kilo mean? 1,000, right? 1,000. Yes, so a kilohertz would be 1,000 hertz, so 1,000 per second. You may have seen megahertz. Mega means 1,000,000, so a megahertz would be 1,000,000 waves per second. Gigahertz, giga means 1,000,000,000, so a gigahertz would be 1,000,000,000 per second. It's the exact same thing as like if in file sizes on a computer, you got a byte, and then a kilobyte is 1,000 of those, or it's a little bit different in computers, but then mega is bigger, and then giga is bigger, and then tera is bigger than that, and so on and so on and so on. You can put all of those on these units. Okay, so here we go. The next important property of light, the one that's going to tie these other two together, is the speed of light, okay? The speed of light. So let me put that right here in the concept pile. The speed of light which is, the variable for the speed of light is c, which you probably have seen in an equation before, by the guy who decided that the speed of light would be labeled with a c. Does anybody know, any of you guys know who decided that the speed of light would be labeled c? It's a very, very famous scientist, and you've seen his equation with c in it, probably. Do you guys know who he is? Yeah, it's Einstein with E equals mc squared. E equals mc squared. So Einstein was using c for the speed of light, and he was the one to figure out something very, very important about light, okay? Specifically about light speed. And this is the important thing about light speed that we've already actually talked about when we were defining a light year. Does anybody remember what is special about light speed? And I'm not talking about it being fast. It is very fast. But what is special about light speed that we talked about before? Guys, remember? Yeah. It doesn't change, right? It doesn't change. It's a constant, okay? All light travels the same speed, okay? All light travels the exact same speed. And that's not true for other kinds of waves, okay? Other kinds of waves can travel all kinds of different speeds, but light is different. It's special. Check it out. What I mean is this. If we're looking right here, if we're talking about water beams, so water waves, one wave could travel fast, and then the next one that came by could travel more slowly, right? Same with sound waves. You could have this one moving fast and this one moving slow. But for beams of light, they're always going to travel at the exact same speed. They all travel at the exact same speed. Okay? Now, why is that important? Why is that important? It means that wavelength and frequency are very, very locked together for a beam of light in an important way that is very easy to remember once we get it, okay? So check this out, and there'll definitely be some test questions tied into this. So, if I am right here, and both of these waves pass by me at the same time, at the same speed, are they going to have the same frequency? If they pass by me at the same speed, are they going to have the same frequency as each other? No, they're not, right? They're not. Because they're stuck going across the page at the same time, at the same speed, one of them is going to send more waves past me per second. Okay, so which one is it? Which one of these will send more waves past me per second if they're sliding past me like this at the same time? Yeah, see how B, because they're closer together, because they're more packed, will send more past per second? So that means, let's take it one step further, if B is sending me more waves per second than A was, which one of these is going to have the higher frequency? A or B? Which one has a higher frequency? B does, right? And if I made another one, let me zoom this out a little bit. If I made another one, so yes, B has the higher frequency. If I made one more in here, and that one was like this, let's say that's C. Would C right there, sorry for ACB, whatever. Would C have a higher or lower frequency than the other two? Would C be higher frequency or lower frequency? It would be higher, yeah, because they're even more packed together. But C has a higher frequency. What about wavelength? What about wavelength? Would wavelength here be longer or shorter than A and B? Would C's wavelength be longer or shorter than the other guys? Shorter. That's right. So, what can we say here? Here's what we can say. If we have a longer wavelength, we have a lower frequency. A shorter wavelength is a higher frequency beam of light. You can't say that for other kinds of waves necessarily, because other waves can go different speeds. But for light, longer wavelengths mean lower frequencies. Okay, so if you compare a bunch of kinds of light, the longer the wavelength is, the lower the frequency is gonna be. Okay? On the other hand, if you have two beams of light and their wavelength is the same, what can you say about their frequencies? If you have two beams of light and they have the same wavelength, what's true about their frequencies? They would also be the same. So two beams of light with the same wavelength have the same frequency, and longer wavelengths mean lower frequencies. Okay? Correct. All right. One last property of light we need to talk about, and that is... Oh, and actually, you know what? Before we go on too much further, I do want to give one quick equation. Here we go. One quick equation. C equals lambda times F. C equals lambda times F. Okay? I'm getting some weird lighting coming in right now. Well, what can you do? Okay. Now, so here, C is the speed of light, lambda is wavelength, F is frequency. Okay? But C can't change, right? C cannot change. That means that C is always the same number, which means if you multiply wavelength times frequency, you should always get the same number, right? You should always get the same number. Now, what does that tell us? Let's figure this out. Here we go. If we need it to always come out to the same number, if we were to take this wavelength right here and make it bigger, what would F have to do? Hi, guys. What would F have to do in order to keep the total the same? Yeah, if you made this one bigger, if you want the total to stay the same, or technically it's called a product, it's not a math class, then F would have to get smaller to make up for it, right? And vice versa. If we made lambda smaller, F would have to get bigger. But that means this equation right here says the exact same thing we just said. If the wavelength gets longer, what has to happen to the frequency? If the wavelength gets longer, the frequency has to get lower, right? So that's the same thing we just said in equation form, okay?